Physics part 387, and now we've got section questions for you. Number one, you are provided with a radioactive source which could be emitting alpha particle or beta particles or radiation or any combination of these. Describe a simple experiment based on their relative penetrating qualities you might carry out to determine the nature of radiations being emitted. Number two, explain the changes that take place to the nucleus of an atom when it emits A, an alpha particle, B, a beta particle, C, radiation. Question number three, complete the following radioactive series. We've got next section, and this is called random decay. Let's move on to the next section of nuclear physics, and it's called random decay. At the end of this section, and then the other one, the following section, you should be able to define half-life. You should be able to define the terms activity and decay constant and recall and solve the problems using A is equal to alpha into n. You should be able to infer and sketch the exponential nature of the radioactive decay and solve the problems using relationship x is equal to x naught expo into alpha into t, where x could represent activity, number of undecayed particles or received count rate. You should be able to solve problems using the relation sine into 0.693 over t into half. We now look at some of the consequences of random nature of radioactive decay. If six dice are thrown simultaneously, as shown in the figure, it is likely that one of them will show a 6. If 12 dice are thrown, it is likely that two of them will show a 6, and so on. While it is possible to predict the likely number of sixes and that will be thrown, I beg your pardon, it is impossible to say which of the dice will actually show a 6. We describe this situation by saying that the throwing of a 6 is a random process. We call it a dice experiment. In an experiment similar to one just described, some students throw a large number of dice, say 6,000 each time a 6 is thrown. That dice is removed. The results for the numbers of dice remaining after each throw are shown in the table. This is the statistical value over here. Number of throws, number of dice remaining, number of dice removed. So 0, 6,000, nothing, no dice removed. 1, 5,000, 1,000. 2, 4,173, 827. 3, 3,477, 696. 4, 2,897, 580. 5, 2,414, 483. 6, 2012, 402. 7, 1,677, 335. 8, 1,397, 280. While the figure is a graph of the number of dice remaining against the number of throws, the kind of graph is called a decay curve. The rate at which dice are removed is not linear, but there is a pattern. After between 3 and 4 throws, the number of the dice remaining has halved. Reading values from the graph shows that approximately 3.8 throws would be required to halve the number of the dice. After another 3.8 throws, the number has halved again, and so on. So it gives us the value of the random probability, and we have put it in a graph in a table in a particular demonstration.